Hello, this is Dr. Strickland. In this video, we will investigate part 1 of the effect of substituents on orientation. Take a minute to read through this one student learning objective. These are the things you should be able to do by the end of this video so that you're ready for the things we will do together in class. Now, the substituents that can be attached to a benzene ring are classified either as ortho-para-directors or as meta-directors. And what we're going to do is take a look at how putting the second substituent in the ortho, the meta, or the para position impacts the stability of the intermediate rhenium ion. So we're going to walk through that piece by piece and see what we see. So let's set up here for 3 cases. There's the ortho option, the meta option, and then we'll set up to do the para option. So in every case, we're going to start the same way. We're going to say, okay, if we've got anisole, which is the benzene ring with the methoxy group attached to it. All right, and I'm going to draw in all of the hydrogens that are attached to those other ring carbons. If this reacts with the electrophile, what happens next? Now we know that in nitration, the electrophile is this guy, the nitronium ion. And so, hold on, need those little non-binding electrons there. All right, electron movement looks like that. So if the nitro group goes to one of the 2 ortho locations, which would be either here or here, then what does the intermediate look like? All right, so I've chosen this ortho position, and so these electrons will be used to form a new bond between this carbon and that nitrogen, which will leave the positive charge down here on this carbon. All right. So in that case, the rhenium ion intermediate looks like this. All right, so nothing has changed in this part of the molecule. So I'm just going to draw everything the way it was. All the changes are happening at these 2 carbons right here. So this one, we said, was left with the positive charge, and this one got the electrophile. And I'm going to collapse it down to NO2 just to keep it out of the way. So this rhenium ion intermediate can be stabilized by different resonance contributors. And you can see that you can move this pair of pi bonds down to an adjacent bond, and that moves the positive charge from here to here. So let's see, so that changed. The positive charge went there. That one's still there, and all the atoms are exactly where they were. Because remember, in a resonance contributor, the atoms don't move. Electrons move, but the atoms don't move at all. And then we can move this bond over. The more resonance contributors there are, the more stable an intermediate will be. And also there are features of resonance contributors that can make one more stable than another. Now, we haven't talked about that in a while, but we've talked about it before. And so this would be a good time for you to get your notes out with the chapter where we did that. All right, so we're up to 3 resonance contributors. Now it turns out that because the positive charge is on the carbons adjacent to the oxygen can actually use a pair of non-bonding electrons and make a 4th resonance contributor, like this. And that moves the positive charge up onto the oxygen. And all the atoms stay in the same place because with resonance contributors, the atoms never move, ever. Okay, so 4 resonance contributors for the ortho option. The interesting thing about this one is that it's the only one of the 4 where every carbon, oxygen, and nitrogen has an octet. So that makes this resonance contributor particularly stable. So extra stable. Because all carbons, oxygens, and nitrogens have an octet. In this one and that one and that one, there's a carbon that has a positive charge. And it has a positive charge because it has an incomplete octet. Incomplete octet makes a resonance contributor less stable. So because of that, this is a special thing. All right, so let's do something similar down here with the meta option and see how that compares. We're going to start off the very same way. We've got anisole methoxy group attached to a benzene ring. And now we're going, okay, what if the incoming substituent were to attach to one of the meta positions? And there are 2 of them, one there and one there, relative to the carbon where the substituent is bound. So same electrophile, same reaction. Just a question of where is this incoming nitro group going to go? If we want it to land here, we can use this pair of electrons still, and we're just switching where the bond forms to the nitrogen and where the positive charge lands. All right, so let's see what this intermediate looks like. So all these parts stay the same. Here, 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 and down here. Now we're going to attach the nitro group to a metacarbon, and the positive charge went there. Okay. So we want to do something similar. We want to move these electrons around the ring, draw some resonance contributors, see if this substituent can be involved in the same way it was with the ortho option. So if we move this pi bond to the adjacent bond, then we get to this. Switches those places. Everything else stays the same. All right. And then we can do one more electron movement. All right, so I want you to pause the video, do the next electron movement around the ring, and draw the resonance contributor. And then come on back. Okay, welcome back. So we can definitely do this. If I move this pi bond to the adjacent bond, then now this carbon will have 4 bonds. Positive charge is gone and the hole is over here. So that one would look like this. So this changed. This one stayed the same. And every one of these resonance contributors that we've drawn so far has one atom that has an incomplete octet. Now you notice that the positive charge never did land on the carbon adjacent to the oxygen. So this one does not have a fourth extra stable resonance contributor. All right, take a look at the para, and then once we've got the three of them, then we can draw some conclusions. One more time. Let's set up our anisole. What we're doing is we're gathering the evidence to support what we see in the lab. We know what it does. The question is, why does it do it? So where is the para position? Okay, so there were two orthos, there are two metas, there's only one para. It's right there, right directly across the ring. And so if I want to make the new bond between this carbon and that nitrogen, I'm going to have to use that pair of electrons to do it. Let's see what that rhenium ion looks like. Okay, so we attached it there. Everybody else has the atoms that they started with. Let's see where the electrons went. That bond and that bond are still where we left them. This is the one that has the incomplete octet. All right, so we can move the electrons. First of all, like that. All the atoms now stay exactly where you left them because we're just doing different resonance contributors. All right, let's see where everybody went. This one's still the same. These two kind of switch places. All right, now we do have a positive charge that's on the carbon adjacent to the oxygen. So that will result in an electron movement like that. Positive charge goes on to the oxygen. Atoms all stay in the same places. Let's see. Okay. And this one stays where it was, and that one stays where it was. So this is one of those extra stable ones, like we saw up in the ortho option. So we will circle that. It's stable for exactly the same reason. It has a complete octet on every carbon, oxygen, and nitrogen. Now there is one more thing that we can do, and that's this. All right, so I want you to pause the video and complete this resonance structure and then come back. All right, welcome back. So let's see what we've got here. I'll put the atoms in first, and you don't have to, but that helps remind me that the atom positions don't change when I'm going from one resonance contributor to another. All right, so this one went here, positive charge went here, and that one didn't change. All right, so the ortho and the para options both have one of these super stable resonance contributors, but the meta option does not. And we think that that is the reason why, when you have an ortho-para director, that the incoming substituent goes either to the ortho position or to the para position. All right, so please take a minute, answer the question at the end of this video, and then come on back.